Okay. So can I get you to start by looking at your I-left trig sheet and reminding yourself about the cos A plus B rule, okay, which is on the formula sheet, so that's nothing that needs to be remembered, but it's also on the I-left trig sheet. So just write out what the formula sheet tells us cos A plus B can be written as. Okay, now what this question is saying, by writing 3 theta as 2 theta plus theta, so what I'm going to do is I'm going to make A equal to 2 theta and B equal to theta. Same angle, just single and double, which is actually the same as 3 theta. So can I get you to rewrite that rule, but replace A with 2 theta and B with theta? Okay, now this question is a show that, which is very similar to a prove. We want to make this, and that's what we've got there. That's an expression of cos 3 theta. We want it to equal this. And I note that I've got a sine 2 theta and a cos 2 theta in there. Everything here is in terms of theta, so I know I'm going to be reaching for my double angle identities. And the first bit, well, I feel confident to do for you. There's only one way of rewriting sine 2 theta, that's 2 sine theta cos theta. And I'm multiplying that by another sine theta. Cos 2 theta has got 3 ways of writing it, but I can't help noticing that in my answer here, everything is in terms of cos. So I'm hoping that's going to help you choose which of the cos 2 theta identities you're going to use. So see if you can replace cos 2 theta with the correct identity. It's being multiplied by cos theta. And then see if there's any simplifying that you can do along the way, maybe looking at the second term there as well. Keep an eye on what you're aiming for. Keep your eye on the prize that we've got there. And yeah, I'll give you a minute just to see where you get to. Now I don't quite feel the proof relief yet, but I've got a cos cubed theta, because when I replaced cos 2 theta with 2 cos squared theta minus 1, and then multiplied that by another cos theta, that gave me a cos cubed theta. Not the right number, I need 4 of them, but that's, that's okay. I've got a cos theta, and I need minus 3 cos thetas, but that's okay. So this is looking okay. This is a bit troublesome, because I noticed that I had a sine theta there, multiplied by another sine theta there. So remember, that's what sine 2 theta is equal to, but it was multiplied by another sine theta, so it gave me sine squared theta. So this is the trouble at the moment, isn't it? Because I want it all to be in terms of cos, and I've got a sine squared theta there. So Harry, what can I do? How can I deal with that particular problem? What can I replace sine squared theta with?
Cos squared. And 1 minus cos squared.
1 minus cos squared, that's right. Yeah, now, so what I'm going to do is I'm going to write these two terms again. These are all looking nice. Yeah, I'm going to now, just to make it a little bit easier to get my head around, I'm going to write this as 2 cos theta, or minus 2 cos theta, times sine squared theta, which is 1 minus cos squared theta. So I've sort of moved the cos theta to there. Perhaps I should have done that to start with, and replaced sine squared with 1 minus cos squared. And yeah, I'm starting to feel that proof relief now, because there's definitely going to be some more cos cubed thetas coming my way, aren't there? See if you can multiply that. Just be careful, this is a minus sign, so it's going to be minus all of this. So it's going to be minus 2 cos theta times that, and minus 2 cos theta times that. So just watch out for that. That's a potential banana skin waiting for you. Did you spot that that's a plus? Because it's minus 2 cos theta times minus cos squared theta. So that's why it became a plus 2 cos cubed theta. Now I'm happy, because I've got altogether 4 cos cubed thetas, and I'm taking away in total minus 3 cos thetas, 1 there and another 2 there. And the 2 most beautiful words in the English language. As required. And that expansion is a really good one to do as part of training. So, if you like to get up in the morning and do a few little exercises, a few sort of sit-ups, a few push-ups, and maybe a bit of the stretching, or maybe yoga's your thing, I don't know. This is the sort of the maths equivalent of a little bit of morning yoga. Get up and do a cos 3 theta expansion, because there's so much going on there. You're reminding yourself about the cos A plus B expansion. You're using both double angle identities, cos 2 theta and sine 2 theta. And of course the nice thing is, and it's always been the case in questions that's cropped up, they give you what you're aiming for. Now, there's a part B here, isn't there? This is a classic hence question, where normally this thing would crop up in an equation, and they'd be asking us therefore to replace it with cos 3 theta. Not the case in this situation. This thing here seems completely different to the thing we've just proved cos 3 theta is the same as. I've got the plus 1 there, which is extra, but looking at this, it seems quite different to this, doesn't it? So this is a bit of a confusing hence question. They've used the word hence, so it must be linked. So can anyone suggest what the link is between what we've just been working with here and what we've got here?
It's minus 2.
Say again, sorry?
Divided by minus 2.
Yes, it's doubled and multiplied by minus 1. It's multiplied by minus 2. Brilliant. Yeah, can we see that? This multiplied by minus 2 gives us this. I know it's written in a different order, but it's true, isn't it? So what that means is I've just shown that this is cos 3 theta. So what that means is this is minus 2 cos 3 theta. Plus the 1 equals 0. So, yeah, the plus 1 isn't part of that, is it? So that is minus 2 times that. So it's also minus 2 times that. We've just shown that those two things are the same. And this is a classic A-level hence bit of misdirection, where it just looks a little bit different. But the good news now, because cos 3 theta is the only variable in this, I don't need to do any identity nonsense. I can just do a little bit of algebra. I end up with cos 3 theta is a half. Sorry, it's barely visible, but there we go. Cos 3 theta is a half. And I can just do shift cos of a half to get what 3 theta is. Now, theta is between 0 and pi, 0 and 180 degrees. So 3 theta, I need to go all the way to 3 pi. So I'm dealing with cos. So that's 1.5 full cycles. So that's 1 full cycle and then half a cycle. That's going to give me my 3 theta solutions, which I'm just going to divide by 3. So go on, do shift cos of a half. You're looking for 1, 2, 3 solutions in that range. Slightly awkward because we're dealing with radians. So make sure you calculate it in radians. Get your 3 theta solutions. There's 3 of them. And then divide them by 3 to get your theta solutions.
So,
Yes.
you know, you changed the first one to the second one by changing it by minus 2.
Yeah.
Where did the cos come from? Why did it change?
So minus 3 cos has become 6 theta has become 6 cos theta.
Mm.
So that's multiplied by minus 2, and that's become that's multiplied by minus 2.
Yeah.
In part A, we've just shown that this is the same as that.
Yeah.
So minus 2 times that is the same as minus 2 times that, which is what I've
Yeah,
written
no,
there.
but I mean, so minus 2 times 3 theta. I get that bit. But
Yeah.
Where's the cos come from? Why is it times by minus 2 cos?
Well, no, this is the same as cos 3 theta.
I just misread it. Yeah, sorry.
Not 3 theta, cos 3 theta. So I'm minus 2 times that is what I'm dealing with.
Okay, yeah, sorry.
We're going to do a second one in a minute, which hopefully will make it a little clearer maybe. Yeah, so it's always a bit awkward when you're in gradients. Remember, 1 full cycle is 180 degrees, it says 360 degrees, 2 pi radians.
What's that?
So my first solution is pi over 3.
Oh, I just can't read it.
So that
Red.
is 2 pi, the end of the first cycle is 6 pi over 3.
Yeah.
So my solutions are going to be a third this side of that, which is 5 pi over 3, 5/3 of pi, and a third that side, which is 7/3 of pi. And I just divide that by 3 to get my theta solutions. Now it seems weird at the moment, but I promise you, if that crops up in the summer, you'll punch the air because you'll be so used to doing it. It's quite a nice standard definition, a standard proof. Now, of course, as is so often the case, we have the evil stepsister of cos 3a to deal with. That's sine 3a. So let's have a little look at that one. Very similar question in that you've got the proof to do first, which this time is all in terms of sine. But then you've got a hence question, and I can't help noticing in my hence question that this is different to this. We're dealing with sine this time, so we need to start with the sine a plus b formula. And they're using a and 2a, which is a little confusing potentially, but I'm sure you'll cope. So look at your iLab sheet for your sine a plus b formula.
Isn't it weird how like people came up with this, and it all like works?
I know. Well, yeah. I mean, you've got to remember, there's an awful lot of people studying maths, even now, and there've been an awful lot of people studying maths for a long time. And these sort of trigonometry definitions date back to the dim, distant times. So Newton would have had these, and Leibniz would have had these, and I realise it's so abstract, but I promise you that those who go on to university and engineering and things like that, it will crop up every now and then. You'll think, oh yeah. Some of you won't. Some of you become PE teachers, but there you go. You never know, do you? You never know. The reason I love it is though because it's such a transferable skill. It's about pattern recognition, spotting something that you've come across before, applying it in a different context. I think it's really, really worthwhile. So you're going to replace A with 2A and B with A, which is potentially confusing, but there we go, I'm sure you can. Again, there's sine 2a there, only one way of rewriting that. Cos 2a is there, 3 ways of writing that, but I've only got sines in my answer. It's great maths, isn't it? In my mind, it's like one of those films where the misunderstood maths genius stands at a board, and the music swells as the professor comes in and says, "It's amazing," Anyway, so I replaced. That's just my funny little dream life. So sine 2a is 2 sine a cos a. Multiplied by the cos a that's already there gives me the cos squared a, which I replace with 1 minus sine squared a. Why did I replace it? Well, because I've only got sines in my answer. Over here, cos 2a, I replace with 1 minus 2 sine squared a. How did I know to choose that one? I've only got sines in my answer. Multiply that out, and this one's a little bit nicer because you haven't got the minus in the middle causing you trouble. And I don't expect you to fly through that with the same enthusiasm that I do, but I think that's another one that's worth practicing and worth training over. And those 10 minutes you sat in your tutor, why don't you try and knock that out? It's just really good practice. Anyway, here we go. Hence. So there's got to be some link. And again, if we don't worry about the minus 2 root 3, if we just look at this and this, looks a bit familiar. So Pat, can you see how they've gone from this to this?
Times by minus 3.
They've, not minus 3.
Minus 4.
Minus 4, yeah. Minus 4 has become plus 6. Again, they've flipped them around to make it confusing, yeah. So this is minus 4 times this. But because of that sign there, we know therefore that it's also minus 4 times that. So minus 4 sine 3a minus 2 root 3 equals 0. Why don't I need to use any identities here? Well, I've only got 3a, that's my only variable. So I can rearrange it to say sine 3a equals something. Triple my range of values. It's all the way to 6 pi. And then shift sign, work out all my solutions. Bob's my uncle. See if you can finish it off. If anyone, please don't be afraid to ask if there's anything here which, I know it's confusing and complicated, but if there's anything you really don't see, please say. probably going to get a negative answer when you do shift sine of that. I'm using. Actually, sorry, they've also swapped A for theta. I mean, it doesn't make any difference, does it? Sorry. Hopefully that didn't throw you off at all. So you get minus pi over 3, so this gap here is a third of pi, so that gap there is a third of pi, so that's 3/3, so that's 4/3 of pi. And then this is 6/3, isn't it? So that'll be 5/3, yes. And then I've got 9/3 here, so that's going to be 10/3 of pi. And that's 12/3, so that'll be 11/3 of pi. And still going, I've got, that's 15/3, so that'll be 16/3 of pi. And that's 18/3, so it'll be 17/3 of pi. Divide that by 3, it'll be exactly the same fractions with a denominator of 9. Get that nice long list of solutions.
If you mucked up the working it out to the last bit,
Yes.
but still did all the last bit fine, everything, would you still get marks for?
So when you say mucked up the working, I mean,
Like, if you just did one wrong thing, like if you got the wrong cos to x something.
right. I think, I mean, the good thing about these hence questions is that even if you don't get the proof here, if you can spot the link, you can still get that equation there, right? So I suppose I'm hoping that most people would get that statement at the start of part B. If from there you made a mistake, I don't know. So if you got a sine 3a equals something different, but still shift signed your incorrect answer correctly, you might find you got some credit. But I think it will be awkward. So I think you could get marks if you weren't able to do part A, because you could jump in at part B by spotting the relationship there. It'd be problematic. Let's resolve to try and avoid that. Now, you may feel that you're really happy with this whole double angle identity thing. You might feel a bit swamped. I'd say that Mrs. Mogston, I'm sure she won't mind me saying this, but a few months ago, Mrs. Mogston had never run a step in her life. Okay, she's very fit and healthy. She has a little small holding, and she does lots of outdoorsy stuff. Never run in her life. Tuesday night, she ran 5k for the first time, and she came to school on Wednesday absolutely high as a cup. She's an inspiration, absolute inspiration. How did she get from nothing to 5k? Did she just think about it really hard, or say, right, I'm really going to do it one day? No, she didn't. She did loads and loads of practice. So she ran a little bit, and then she ran a little bit further, and she ran a little bit further, and she joined a running club, and then, this is where we come back to this, don't we? So if you're feeling swamped, then do the practice, okay? And one thing she had, she ran with her daughter, who does a lot of running, and encouraged her. So let me be, no, that's weird, don't let me be your daughter. Let me be the person that encourages and supports you. But so, have a go on your own, but then come and ask me when you get stuck. And I'm here tonight. Ironically, I was here last night because they ran out of boosters. But there you go. I'm here tonight, and I'm around any lunchtime. And I'd like nothing more. And I'll be absolutely honest with you. You come to me and you say, oh, that's already open on the screen. I'm really stuck on that one. I'm not going to say, oh yeah, the answer is this and this. I have to roll my sleeves up every time, and I'll work it out with you. These are not easy questions. And sometimes you have to have a punt, and you go down a blind alley, and you have to come back and start again in a different direction. So don't worry if that's what you find happens when you do it. But yeah, I really recommend that you have a go. Actually, Maths Genie, if you look at Maths Genie earlier in this exercise, it does both the Sine 3a and the Cos 3a expansion. So that's in there as well. Right, so we've got time just for me to sort of set up what we're going to do in our next lesson, which is something I call composite trig functions. I'm going to explain what I mean by that.
These the ones in the formula sheet?
These are not. No. No, this is. Okay, so here is, change it to the steps of 16. So here is the graph of sine x, and I could multiply the whole function by something. So this is the graph of 4 sine x and 5 sine x. Looks exactly like a normal sine curve, but it goes from 5 to minus 5, rather than from 1 to minus 1. So that's the graph of 5 sine x. Okay. This is the graph of cos x. It's the same shape as the sine curve, isn't it? It's just been shifted. You could think of it as a sine curve, which starts here, that's been shifted backwards 90 degrees, and I could multiply that by a number. So there you go. Oh, hang on, let me step in. Let's do a step. One, there we go. That makes it a bit nicer. So I can multiply that. So let's have, I don't know. Let's go for 3. There you go. That's the graph of 3 cos x. Just a normal cos curve, 360-degree period, but it goes from 3 to minus 3. And my question is, what if you construct a function that is composed of both of those added together, a composite function? What am I going to get if I add those two functions together? Would anyone like to suggest what sort of shape I'm going to get if I do my first function added to my second function?
It's going to be really steep.
That's suggesting really steep. Lily, a little symbol? What was that little symbol? Okay, here we go. So I'm saying let's take the red line, which is 5 sine x, and the green line, which is 3 cos x, and let's add them together. What do we get? We get the black line, which is another sine curve. It's another sine curve. It's not sine x, because it doesn't go from 1 to -1, and it doesn't start at 0. It's being shifted backwards something. But it's the same shape as the sine curve, so I could say, well, what I've got here is a sine curve that's been shifted backwards a little bit. So I do that by replacing x with x plus something. I'm going to use alpha. And then it's been multiplied by something. I'll use r for that. So this composite function, when you add the two together, gives you a sine function. Now this is really practical because we know that lots of things have sinusoidal waves. Sound, for example, vibration. And we very often have situations where different vibrations or different sounds or other things which move in that way, electromagnetic waves, are being combined. And the combination is always a sine curve. I didn't just luck out and choose one that gave me values. Look, if I change the value of my multiplier for the original sine curve, you still get that sine wave for the black. It shifts slightly differently, and it's slightly different multiplier, but it's still the same. And the same is true with cos. And, and if I change both of them, then the effect. This changes a little bit, and this changes a little bit, but you still get a sine curve. And how we work out this and this is what we need to do. Now, have I got time? I haven't got time. What we're going to do next lesson is I'm going to show you how you can work out, given that, what that is and what that is. And it gets even better, because that black line, I could think of it as the sine curve that's been shifted backwards, but I could think of it as a cos curve that's been shifted forwards. So it could also be written like that. Different value of alpha, same value of r. That's what we're going to do. I can barely wait. Barely wait. Can I encourage you? I tell you what, let's pick one. Let's pick one. Let's pick one from here. Let's do one of the proof questions for next lesson. There you go. It's that lesson where we're in the funny room, aren't we? Where we're in
No.
Now, Chris, you've got solutions, so there's. I suppose you could have a little peek, but these combine the double angle identities with the reciprocal identities. So, shall we ever go at 14b for next lesson? That's on and that's good because that forces you to go to OneNote and sort of open up that document. So we'll have a go at 14b at the start of tomorrow's lesson. We will go through the mechanics paper, but not next lesson because that room's just horrible. So we'll do that next week.